This is my TRB 2023 presentation entitled Estimating the Tire Pavement Grip Potential from Vehicle Vibrations. This work is part of the LIRA project. LIRA stands for Live Road Assessment. It is a proof of concept project to try to estimate road conditions based on vehicle sensors. The partners of this project are Green Mobility. Green Mobility is a company that runs a car sharing service in Greater Copenhagen area. All the cars are Renault Zoe electric cars. Vejdirektoratet, the Danish Road Authority, these are the coordinators of the project. We have the Technical University of Denmark, DTU Civil Engineering, and DTU Compute. And we have Sweco. Sweco is a consulting company that runs the pavement management system for Copenhagen municipality. Again, the idea is to harvest the data from the cars, the green mobility cars that are driving around Greater Copenhagen, and make a live map of the road conditions. There are about 500 Renault Zoe cars that are being driven randomly by customers. Just as a teaser, I can show you the first look at the LIRA map. Here you have the trips, different trips from different customers. And here we have different data or different sensor data coming from the car. Here is an example of one trip. You can see the beginning and end. And you can choose what type of sensor data to look at. For example, this is the accelerometer that records accelerations in the vertical or Z direction. And by pointing at different locations on the chart, you can see where this data was collected from. Another example is looking, for example, at the RPM or the front left tire. Here you can see the numbers here indicate the revolutions per minute experienced by the front left tire of the Renault Zoe for this particular trip. So in effect, we have harvested data from many trips, and these are all georeferenced given that we have a GPS in the cars. As a means of induction, here's a wheel that is moving at a speed s towards the right here, and it is rotating with an angular velocity omega. The wheel has a radius r, and it is moving at the speed s while braking. These two arrows here indicate the forces that the wheel experiences at the tire pavement contact. These are the same forces experienced by the pavement. The friction coefficient is the ratio between the horizontal force in the direction of travel and the vertical force that comes from the self-weight of the vehicle. It is commonly known that if you plot the friction versus relative sliding is defined as the moving speed of the wheel minus the moving speed calculated based on rotation. So this is omega times r, and then normalized by the actual speed of the wheel. If we plot the friction coefficient under these conditions, we have this trend of increase reaching some peak and then decreasing again. Relative sliding equal to 1 indicates that the wheel is locked, and that is where omega is 0, and then you have the speed normalized by the speed gives you the unity. This is also giving us the friction coefficient at the locked wheel conditions. The peak normally happens at around 20% relative sliding, and this is a mu max, and this is what I refer to in this presentation as tire pavement grip potential. The tire pavement grip potential, or mu max, is a safety related feature. It controls stopping distances, traction control, and yaw stability. And research is showing that mu max varies with contamination at the pavement surface, at the contact patch of the tire with the road, the weather conditions, the surface texture of the pavement, tire properties, vehicle speed, and also mu max changes over time with the pavement usage and as pavement's age. The current technique, most common technique for monitoring mu max in a pavement network is to perform periodic skid resistance campaigns. For example, with this type of vehicles, where we have wet surface and other standard conditions under the test. The problem here is that we have information gaps. If we look at a certain section of a highway and ask ourselves how often this piece of the highway is being monitored for mu max, there could be months and even years in gaps of information. Here comes the motivation for this study to get more frequent mu max estimations using in-vehicle sensors. In our case, in the LIRA project, is to use the inbuilt sensors of the Renault Zoe, and then take data from normal usage of the vehicles, not asking the vehicles to perform specific maneuvers. A review of literature shows that there are two categories of mu max estimation. The first one is a model-driven approach, where physics or vehicle dynamics are utilized in order to estimate the friction at the tire pavement contact. And this works where you have high excitation driving, for example, braking, accelerating, or turning. And this is normally utilized for real-time analysis and feedback for the different elements within the vehicle itself. The second category for estimating mu max is data-driven, where we can see statistical or machine learning methods that are applied to estimate mu max. Normally, this is done with special sensors, like sensors that are embedded in the tires, or microphones that are listening to the sound emitted at the tire pavement contact, or video cameras that are installed. These are not normally available in vehicles in general. The specific objective of this study was to outline and validate a new data-driven method for estimating mu max. The method is based on in-vehicle accelerometers. The choice for looking at accelerometers is because they are easy to install also post-production, especially if there is no access provided by the car manufacturer to the inbuilt accelerometers. We can always install our own accelerometers afterwards. And another objective is to have the method applicable to low excitation driving, meaning highway conditions where the cars are driving along a straight line without maneuvering, without braking, accelerating, or turning. The approach that this study has taken is based on the idea that all cars have a toe-in setting, meaning that the wheels are not parallel to each other and do not point in the driving direction, but are pointing a bit inward. And if we have a closer look at what this means, so here we have this arrow indicating the travel direction, the actual travel direction of the vehicle, and here this arrow indicates the wheel heading, and there's a small angle between them. This angle is called the slip angle, and because of this, you could see that the tire threads, this is shown here schematically, are distorted, and this distortion happens due to the fact that the wheel would like to continue in one direction, and the vehicle travels in another direction. This distortion is actually happening at the tire pavement contact, and actually slightly extends over that zone of contact. Here you can see the side forces that are generated because of this slip angle, and the zone of disturbance is shown to be slightly larger than the length of the tire contact patch. Now, the side force intensity is a function of the slip angle, of course, the friction that is available between the tire and the pavement, and also the weight that is exerted on the wheel. And the side force oscillations, which is how the side force intensity changes over time, is in many ways related to the effective texture of the pavement, and also, of course, the speed at which the car travels. Here's a short clip showing how the distortion of a tire looks like from the inside. So here we had a person installing a GoPro camera inside the wheel hub. So you can see the car is driving straight, but every time there is a contact with the pavement, the tire deforms, and also deforms slightly sideways. So the hypothesis for this study is that the transverse vehicle vibrations are related to side force oscillations at least within some frequency bandwidth. So this means that if we are monitoring the vibrations of the vehicle, sideway vibrations, they are related to the side force oscillations that the wheel experiences, at least within some frequency bandwidth. And that means that these vehicle vibrations also carry information about surface texture. And since we know that surface texture and mu max are correlated, then there is some link between vehicle vibrations and tire pavement grip potential. In order to validate the first assumption that vehicle vibrations and side force oscillations are linked, we looked at the P1 instrumented vehicle. This vehicle is currently operating in Bucknell University, and I got permission to use the data from Craig Beal, who works with this machine. This is an electric car. It's a drive-by-wire car, and it is heavily sensed, and all sensors are collected synchronized in a synchronized manner at a rate of 500 Hertz. That's the data acquisition system they have. And specifically, the side forces are monitored with force sensors, and the vehicle also has an accelerometer that measures the sideway accelerations. So this vehicle was utilized to check that vehicle vibrations and side force oscillations are linked. I took a 30-second drive of the P1 vehicle, drive along a straight line at a speed of 36 kilometers per hour, and there was a front slip angle setting of 0.7 degrees. And here's how the transverse oscillations look like versus time for the 30 seconds. They appear to be randomly changing between -1 to +1 meters per second squared. And here you have the side forces recorded for the right front tire, also for the same duration of 30 seconds. So if we look at the acceleration amplitude spectrum and plot it versus the right front side force amplitude spectrum, there is a correlation between them. The correlation is not very high, but it's not negligible. It's 0.55. It's an indication that the accelerations of the vehicle are linked to the side forces that are experienced by the tire. Second part is to validate that vehicle vibrations are linked with the skid resistance. For this purpose, we had a test campaign where we followed the VFRIC, which is a friction measuring truck, with a green mobility car, and the car was driving just behind the truck for a 26-kilometer highway, and the speed was 60 kilometers an hour, and the VFRIC was measuring skid resistance, and we were recording at the same time the horizontal transverse oscillations in the vehicle with an accelerometer. This is a short clip to show how this was carried out. So here you have the green mobility car. There is a GoPro attached to the left front of the vehicle, and it is following the VFRIC. You can also see how the VFRIC is deploying some water here, spraying water, and then at the same time measuring the skid resistance of the highway. In this chart, we have the distance along the measured highway, 26 kilometers, and the skid resistance. And here you can see the measured skid resistance in black and the estimated skid resistance based on the oscillations from the vehicle. And the coefficient here of correlation is, again, it's not perfect, but it's not zero. It's a moderate correlation of 0.47. So just some concluding remarks. It seems that transverse vehicle vibrations can be linked to tire side force oscillations and therefore to tire pavement grip potential. The new mu-max estimation method is deemed potentially useful for pavement management. It's suited for highway conditions where the cars are driving at a more or less constant speed along a straight line. And imagine that you have many cars and you average the results from many of them, then the quality of the estimation can be improved. I would urge you to consult the article for more details. One last note, I was just looking at the statistics, the world statistics, how many new vehicles are entering our roads. And this is worldwide vehicle registrations. That includes private cars, buses, and trucks over time. And you can see that there is a sharp increase in the numbers. We are currently at 1.5 billion vehicles on our roads, and the curve is shooting up high. So this also indicates the relevancy of the study for future years. Thank you very much for your attention, and I urge you to check out the two QR codes here.